Last time to describe the physical spectrum of closed strings, closed bosonic strings. Okay, so let me remind you. So the physical states is this visible from the back? Okay. Okay. So physical states of the closed string are of the form, I'll write them as V, satisfying the following conditions. First, ghost number should be 2. Second, it should be annihilated by B0 minus and L0 minus. Third, it should be BRST invariant. And fourth is the equivalence relation, that V is equivalent to V plus QB lambda if B0 minus on lambda is 0 and L0 minus on lambda is 0. And we also saw examples of states which describe the graviton, dilaton and antisymmetric tensor fields. So today the question that we will be addressing is how to calculate the S matrix of these states. How to calculate S matrix of n such states, which I will denote by V on to Vn. So let me state the result and then I will try to explain the various parts of the result. The result is that if we take G loop n point S matrix is given by an integral over integral, right, integral of for integral is over So punctures are fixed points on the Riemann surface. This is where the operators V on to Vn are inserted. So this is the statement and I will now try to explain various parts of the statement, okay, because many of these things may be not very familiar. So, in particular, we will try to address the following questions. The first is how to describe and when I say how to describe, okay, the specific question that we will try to address is how to introduce appropriate coordinate system, okay, which will be a set of numbers that parameterize points in the moduli space of genus G Riemann surface with n punctures. Because ultimately you are going to integrate over those numbers, right? So, how the coordinate system on the moduli space of genus G Riemann surface with punctures. Then the second question that we will try to address is how to compute correlation function on a genus G Riemann surface. And third is what precise correlation function appears in the integral. Okay. And once we understand these, this gives an in principle definition of scattering amplitudes. Okay, which means in principle then we can put it on a computer and evaluate this integral. Now here I should also add that something that I will not be discussing in these lectures is that there are further issues with IR divergences. There are no infrared divergences in these scattering amplitudes, but there are further issues with IR divergence. Which is resolved using string field theory. Okay. So let me just mention what kind of issues that arise. So basically the worldsheet approach that I will be describing here, essentially you can think of this as a sum of Feynman diagrams. Even though we will not get it as a sum of Feynman diagrams, the worldsheet approach will produce a result that is roughly like sum of Feynman diagrams in a quantum field theory. But in quantum field theory, you know that if we naively have just a sum of Feynman diagrams, that by itself does not always give the correct answer. Okay, an example of this is the following. Imagine that you have a Feynman diagram. Let's say 5 to the 4th theory, and you have a Feynman diagram of this kind. 4-point scattering in a 5-4 theory. Right? So this is a Feynman diagram that you can draw. But if you just naively try to evaluate this using the Feynman rules, what we will see is that you have momentum k here, the same momentum k flows here. Okay. So this propagator gives you 1 over k square plus m square. And this is of course infinity on shell for on shell external states. Exactly. Yeah. So if you use LSD, so that's the correct way to treat this is to use LSD, right? Where you will not include diagrams like this, right? You will resum this and write it in terms of renormalized masses. The worldsheet, okay, what it does is it gives you results which are directly like results for the Feynman diagrams. Okay. But it doesn't know about LSD. Right? The worldsheet gives you the result just as if you are just summing Feynman diagrams. Okay, you don't know anything about LSD, and because of this, if you just naively examine the worldsheet result, you find various divergences of this kind. Okay, and these are what I call infrared divergences because these are coming from some internal lines going on shell. But in quantum field theory, you know that internal lines going on shell means that you are doing something wrong, and you have to repair it. In this case, you have to use LSD, for example. Right? There are other examples where you have to do other things. That is not contained in the worldsheet description. Right? That's the reason why, in order to make sense of the worldsheet results, you have to try to use the language of string field theory. Okay, so this part I am not going to discuss today. Okay, I'll try to discuss. What I am going to discuss is how to just directly write down the expressions for the scattering amplitudes, okay, which is the analog of what you will get by directly summing Feynman diagrams in a quantum field theory. Are there questions? So I'll begin by describing the moduli space of genus G Riemann surface with n punctures. Okay, and punctures are some fixed points on the Riemann surface. Okay, so the MGN is moduli space of whether is this size okay? The is very visible from back. So I'll be using some result here, okay, and that is the dimension of the moduli space. This I'm not going to prove. This is known from various mathematical literature. So dimension is 6G minus 6 plus 2n. Okay, which means that the integral that we are supposed to do will run over 6G minus 6 plus 2n parameters. Okay. So I'll first try to describe how these 6G minus 6 plus 2n parameters arise in the first place. Now, the way I am going to introduce the coordinates of the moduli space is no unique. There are many ways to do it, right? But this will do the job. So, first a claim which can be easily verified. Okay, so the circles I will denote by CS, the spheres I will denote by SI. Okay. And it is best to understand this by some examples. Okay, so I will just pick two examples, but you can easily construct other examples. So take G equal to 0, N equal to 4. Okay, a sphere with 4 punctures. Okay, so here is a sphere with 4 punctures. And so now what you are supposed to do is to draw some discs around the punctures first. So this is D1, D2, D3, D4. Okay. So this produces a sphere with 4 holes, but we want to build things with spheres with 3 holes. Okay. So what we can do is that we divide this into 2 parts. Okay. So here you see that you have on this side a sphere with 3 holes, 1, 2 and 3, and on that side also you have a sphere with 3 holes, 1, 2 and 3. So this we can call S1 and this we can call S2, and how many circles are there? C1, C2, C3, C4 and C5. Okay, so let's check the counting. Okay, so number of discs is of course 4. Okay, that's by construction. Okay. So 2g minus 2 plus n. Okay, g is 0. So this is n is 4. So this is 4. This is 2. Okay, so we need, according to this, we should have two spheres, right? And indeed we have two spheres, S1 and S2. Okay. And number of circles is 3g minus 3 plus 2n. Okay, g is 0, n is 4. So that's 5. Right? So we indeed have 5 circles, as you can see from here. Okay, so that's one example. So here is one more with g equal to 1 and n equal to 2. So we draw discs. Okay, and to create sphere with 3 holes, we have to cut it here. Okay, so we have D1, D2, S1, S2, and circles are C1, C2, C3, C4. Okay, and we can now check. So this is G equal to 1, N equal to 2. So N equal to 2 means 2 discs. 2G minus 2 plus N, that is 2, right? So you should have needed 2 spheres, and indeed we have 2 spheres, S1 and S2. And the number of circles, 3G minus 3 plus 2N, that's 3 minus 3 plus 4. So this is 4. And indeed we have 4 circles, 1, 2, 3, 4. Okay, and this you can check for any genus Riemann surface with any number of punctures. So this is the way we can decompose the Riemann surface. Okay, again this is not unique. You can do it in many different ways. Okay, but this is just one way to introduce coordinates on the moduli space. Okay, I have not done it yet, but I am going to do it soon.
The circles on the disk means the boundary of the disk.
Circles, no, the discs themselves are in the interior. Circles are the boundaries. Yes, indeed. So I should have maybe written the D inside this, right? But the space is too small. But discs are just the whole thing.
And join means either join to circles join to each other or to the puncture.
To the no, circles are joined to each other, right? Because well, the D and S1 are D1 and S1 are joined all along C1. That's what I meant. It's joined at the circles. Yeah. So discs and the spheres, those are the two-dimensional surfaces, right? They are joined along the circles. So we'll introduce coordinates. So WA will be the complex coordinate on dA. Such that the eighth puncture is at WA equal to 0. Okay, so origin of WA coordinate system is a special point where the punctures are inserted. Otherwise, WA can be arbitrary. Okay, it it's a one-to-one representation of the points inside the disk, but otherwise there is a constraint on what WA is. Similarly, we can introduce coordinate of the sphere. Zi are the coordinates on the sphere. Yes, sir. And the moduli of the Riemann surface, that information is encoded in the transition functions across the circles. Right? That's the statement that WA and Zi are related by certain relations along the circles, right? And those are the ones, those are the functional relations that capture the information about the moduli space of the sphere. Yes. No, not necessarily. Yeah, because on the sphere there is really no preferred point, right? The punctures are special, right? The WA, these have to add WA equal to 0. On the sphere, it's not fixed. Okay. So one would expect that there is a relationship between the coordinates on the two sides of a circle, okay, and that relationship should be analytic in a small band around the circle, right? That functional relationship doesn't have to be well defined everywhere, okay, but it should be well defined around in a small band around the circle, right? So that's the meaning of there should be an analytic relation between the coordinates on two sides of the circle.
We know that in the conformatic we can fix the point on a sphere using conformal symmetry, right?
Yes.
Why is it important that we need a transition function between the disk and the sphere to the circle?
Well, we'll see when we come to sphere. I'll look at the example of a sphere, right? The sphere will also be described in this language. Okay, because when you write down the integration measure, it's useful to use a common language, right? So we'll describe the sphere in this language. We'll see how it comes. So we'll choose some orientation on the circles. Okay, it's arbitrary, up to us. Choose some orientation on CS. These can be independently chosen on each circle. And we'll define by sigma s the coordinate on the left of CS and by tau s the coordinate on the right of CS. And we expect that sigma s will be some function of tau s. This function is analytic in a band around CS. No, no, no. Spheres are the SIs, two-dimensional surfaces, right? The SIs are the spheres with holes, right? So, so at this stage, we are all in two dimensions, right? We will see how the 6g minus 6 plus 2n comes. Right? We will not describe how it comes, but we will see how to introduce coordinates in that space. Okay. Right now, we are dealing with all two-dimensional spaces. Is this clear? Other questions? Right. So all you have done here is that you have a two-dimensional space. We have divided it into many regions, and you are introducing the coordinate system, that the transition between the coordinate system between those regions, right? Those are the FS. So now I can give a definition of MGN. So MGN is the space of FGN, the space of the transition functions up to equivalence relation induced by coordinate transformation on SI and D, keeping the eighth puncture at the origin of DI. Okay, so let me explain what I have said. So we have these transition functions, Fs. Now we can make a change of coordinates zi going to a function of zi. We will demand that that change of coordinates should be one-to-one on SI without the on SI, right? But it can be singular outside these holes, right? We don't care if the coordinate transformation becomes singular outside these holes, okay? But SI with three holes, right? It should be non-singular in this region. Okay? Similarly, the coordinate transformation that you make on the disk, okay, should be non-singular inside the disk, okay? But it should also have an additional property that it should take WA equal to 0 to W prime equal to 0. Okay, so those are the coordinate transformations we'll be allowing. Okay. And now I'm saying that we have, sorry, space of Fs, not Fgn. So we have these transition functions, okay, which is infinite dimensional. You can take the transition functions to be anything that you like, right? Well, not almost anything that you like, but certainly there are infinite number of possible choices. Okay. Similarly, there are infinite number of possible coordinate transformations, right? You take zi to any function of zi, right? It's not, it doesn't have to be SL2C, right? It can be any function of zi because you have cut out three holes, right? So function is allowed to be singular outside those holes, okay? And then you take the quotient, right? The in equivalence classes of transition functions. That is what describes the moduli space of genus G Riemann surface with n punctures, and that dimension is given to be 6g minus 6 plus 2n. Okay, this is not what I'm going to prove. This is known to be 6g minus 6 plus 2n dimension. No, I don't think there is a, I mean, not using this. There is a Riemann rock theorem which you can use to do the counting, but just from this description it will be very hard to do the counting. Yes. Equivalence relation is that if you take, suppose you have taken one set of transition functions, right? Now you change the coordinate zi to some function of zi, right? That will change the relationship between zi and w. So it will be give a new set of transition functions. Those are declared to be equivalent to the original one, right? Because changing coordinate system shouldn't change the surface, right? So that's the equivalence relation, that any change of coordinates inside the disk or inside the sphere, right, which are non-singular in their respective domains, okay, is allowed, and that can change the transition function, but that new transition function is declared to be the same as the old one. That's the equivalence relation. And the non-trivial statement is that the set of all transition functions modulo this equivalence relation is a finite dimensional space, and that dimension is 6g minus 6 plus 2n dimension 2n. So a label then Fs, instead of writing is Fs of, well, what did I write there? Sigma is, yeah, Fs of tau s. Okay, instead of writing it this way, we'll write this as Fs of tau s and u, where u1 to u 6g minus 6 plus 2n are the coordinates on the moduli space. Okay, we write it this way because by changing u, will change the transition functions. Okay, and those changes are supposed to be produce non-trivial changes, right, which cannot be undone by coordinate transformation. Okay, so that's why I am going to put an extra label u in the transition function. Okay. Now the question is, what is that? Is there a procedure for choosing these u's? Right? And the answer is that basically anything that you do will work, right? Unless you are lucky, unless you are unlucky, right? Because you see, you have an infinite dimensional space, right? And you have another infinite dimensional space by which you are quotienting, okay? But the one that you are quotienting by is 6 is less dimensional than the original one, right? Original set of FSs. Okay? So if you randomly choose some parameters inside the function, right, it's likely that those parameters will actually give a non-trivial deformation, right? I mean, what are the chances? I mean, it's like the ones which are pure gauge, right, which can be undone by coordinate transformation, is a codimension 6g minus 6 plus 2n in the space of all transition functions, right? And if it's codimension 6g minus 6 plus 2n, then any random variation that you take is likely to be not in that subspace, right? Because it will be outside the subspace. So any parameterization that you use, unless you are unlucky, is sufficient. Okay, and I'll now describe some particular way of parameterizing. So you consider a particular parameterization. So we describe the ith sphere, describe SI as by coordinate ZI with holes around 3 points, right. So let's call them AI1, AI2, AI3. Okay, so the ith sphere, okay, which you can represent as a complex plane, okay, basically has holes cut out around AI1, another sphere hole around AI2, another one around AI3. Okay. And now we label the transition functions as follows. So if the circle around okay, which means that when you glue the WA disk, right, you simply declare the ZI and WA are the same up to the shift, right, so that the puncture sits at ZI equal to I1. Is clear? This is my choice, right? I am declaring the transition functions to be this way. I just have to introduce somehow 6g minus 6 plus 2n parameters, right? And which is what I'm going to do. If the circle around let me call this, so the Q's don't get confused, let me call this something else S or T maybe. Okay, I identify the Zi and Zj coordinate by a relation of this kind, where Qs is a complex parameter. Yes, indeed. Because on the jth sphere, right, I choose these to be AJ1, AJ2, AJ3, right. Ith sphere may have a different one, right. So so on this side we have both I, right, Zi minus AIP. On this side you have Zj minus AJT. With this is relation in different spheres, exactly, right. So we have two spheres, say here, right, this is S1, this is S2, and I am telling you how we should identify the coordinate Zi with the coordinate Zj. Okay. Zi, this circle on the Zi plane, on the Zi plane is around Zi equal to I, okay, and this circle is around Zj equal to Aj. Okay. So you see from here that as Zi approaches AIP, Zj goes away from Ajt, right. So it's like there is a circle, as you are going towards the center of the hole from one circle's perspective, from the other circle's perspective you are going away from the center of the hole, right. So as you go in from one side, you come out from the other side. Pardon?
So the common of the sphere, the AIP and AJP or
Yeah, so for the common circle, you can of course define various ways to common circle, but let me do it one way. Pardon? QS. This is QS. QS is the will be the parameter. Okay. So one way to write this is that mod Zi minus AI P equal to mod QS to the half is joined to mod Zj minus Aj T equal to mod QS to the half. Right. So on the first sphere there is a circle of radius mod QS to the half radius. On the second sphere also you have a mod QS to the half radius. This circle is on Si, this circle is on Sj, okay, and these two are glued, right. So which means that as you see here, as you go in from outside of the sphere, here you come out, right, because as mod Zj minus Ajt is, when this is decreasing, the other one is increasing by this relation, right. So as you go towards the hole, towards the center of the hole from one side, you come out of the center of the hole from the other side, right. That's the sense in which they are glued. Okay, you go in from here and you come out from there. Pardon? You can choose, yeah, given a Riemann surface, yes, there is a you can choose any holes, right. Those may describe different Riemann surfaces, right, if you choose different holes. So the way we are going to introduce the parameters, okay, is that we will treat these QSs as parameters. Okay. So let's say how many such parameters we have. Okay. To begin with, we had 3g minus 3 plus 2n circles, right? Of which n of them n are joining Si to Di. They are of this kind. We said somewhere, or did I erase it? That across the disks, yeah, we had said, but maybe I didn't write it. Zi is equal to Wa plus I1, right? If when you're gluing disks, okay, the ds to the SIs, we don't introduce any transition function, right? We don't introduce any parameter. We just take the transition function to be simply given by this, right? So that the Wa equal to 0 gets mapped to Zi equal to A1I. So non-trivial ones come from here. Okay. So that gives you, this means we have 3g minus 3 plus n q's. Okay, because n of these are gone. So you have 3g minus 3 plus n q's, and those you can treat as 6g minus 6 plus 2n real parameters, which are the moduli, which you can take to be the local coordinates on the moduli of the Riemann surface of MGN. Is this clear? Now this is completely arbitrary, right? I have just chosen one example to illustrate, right? But you could have introduced these parameters in many different ways, right? You could have, for example, introduced these parameters through the relation between Zi and Wa instead of between Zi and Zg. Any question? Yeah. So number of circles was 3g minus 3 plus 2n. Okay. And now we are introducing one q for every sphere to sphere transition function, right? Now of these 3g minus 3 plus 2n circles, n of them are sphere to disk transition functions, right? So on those you don't have any q's, right? So we are left with 3g minus 3 plus n circles which are sphere to sphere transition functions, and that's where I am introducing these q's. Clear? Pardon? Yeah, so at this stage they can take any value, right? Now, as I said, you can also join the surfaces in different ways. Given a Riemann surface, this decomposition into how to decompose into spheres plus disks is not unique, right? You can cut it in different ways. Okay? You can introduce parameters that way. So together they combine the whole moduli space. Okay? But to determine what are the inequivalent points in the moduli space requires more effort. Right? But there are standard mathematical procedure, but that allows you to do that. That imagine that you have one set of q's and another set of q's. You can ask, are they describing the same point in the moduli space or different point in the moduli space? Okay. So there are some tests that we can do to figure out whether they are describing the same point or the different points. Okay. So in general, we will let these q's take arbitrary values, okay, but not all of them are inequivalent. Yes. Exactly. So you have to do the utilization of q variables and the range of these variables. You have to fix separately, right? As I said, that there are some various mathematical identities that you can use to determine which are whether you are covering the same point in the moduli space more than once. Okay, which are basically the period matrices. I mean, on a torus, for example, right? We know that the moduli space. I mean, the periodic identification, right? If you have torus with some n punctures, each puncture, right? Once you go around either the A cycle or the B cycle, you come back to the original point. Similarly, on the torus moduli, right, there is the SL2Z transformation, right? You have to mod out by those. So all those are contained separately in, as I said, by these various tests, right, as to when they describe inequivalent points. So what I'm describing here is a way to introduce local coordinate system in a moduli space.
And those two, so continuing this question, so if you think of Q as some complex numbers, can we always think of them as some portions of the T to the?
No, it's not. No, it's not very simple. No. Yeah. So typically, what for every set of Qs, you can calculate the period matrix, right? And then you have to check that you are only integrating over the inequivalent period matrices. Yeah. So there is a simple way to characterize the global structure of the moduli space. Right? That's why in higher genus, okay, the global structure of the moduli space is very complicated.
Is it fair to say that the non-trivial transition function always creates here, or is it the consequence of this?
No, it's a consequence of this way of parameterizing. You can show that all the non-trivial transition functions can be encoded in a single sphere to disk transition function. Okay, if you take say just z to w, right, and allow this function to have poles at the origin, because this function has to be only well defined on a strip, right, on a ribbon, right? So it can have poles inside, right? You allow the function to have poles. So the complete 6g minus 6 plus 2n moduli can be absorbed, can be encoded in just a single transition function. Right. So that's why I said that almost anything that you do is good enough. Okay. And the procedure that I'll be describing will not explicitly rely on this construction. Okay, the integration measure that I'll be writing down for the that what you have to integrate to get this S matrix. Yes. Yes. Yes.
So if the volume of the flat is finite, then there is no problem.
No, but volume of the large GPU is not finite. No, because SL2Z, for example, is an infinite dimensional group, right? So you really have to mod out by the modular group. No, I said AI1 because the Zi, right? So I already assumed that Zi is glued to the Si is glued to dA, right? And the particular circle that glues is a circle around AI1 in the Zi plane. Okay. I had written it somewhere, but I think I have erased it somehow. Okay. So the point is, let me do it again. That we have the transition function between Si and dA, right? We are saying that take a particular circle of Si, which is the circle around AI1. Okay, because AI1, AI2, AI3 are the three holes, right? The points around which you have drawn the hole. Take the particular circle around AI1, right? And then glue that to dA by this simple relation. Okay, but this is completely our choice. I could have put, as I said, all the moduli in this transition function by making this more complicated. Yes. No, it's not. Yeah, it's not Schottky parameterization. There you start from the upper half plane and identify. So this is some generic parameterization, right? And as I said, the moduli space measure that I'm going to write down will not depend on that parameterization. Okay, so far I described how to introduce coordinates in a moduli space. Okay. So what I'm going to do is to skip the second part for now. Okay, which was to how to define the correlation functions on a Riemann surface. Okay, I'll come back to this later, maybe later today or next time. Okay, but I now jump to question 3. Okay, and that is that what correlation function do you have to compute as what correlation function gives the integral? Okay. This is the integrand that will appear in the expression for the S matrix, right? Because I said that S matrix is an integral over the moduli space of Riemann surfaces, okay, and you want to know what is the correlation function that you have to integrate. So we'll take U1 to U6G minus 6 plus 2n as the moduli. Okay. And as I have said earlier, the way we had introduced this moduli is through the transition functions, namely that when we relate the coordinates on the left and right of that circle, Sth circle, I write sigma s equal to fs of tau s, but these functions have implicit dependence on the moduli. So what we are going to do is to try to introduce a 6g minus 6 plus 2n form on this moduli space, because then we don't have to worry about the measure that we should use to integrate, right? If it's a form can be integrated naturally on a on the corresponding moduli space. So that's what I'll try to do. Okay. So we need a 6g minus 6 plus 2n form. Okay, now some definition. So what this says that you take the derivative of fs with respect to u, okay, and this derivative is to be taken at fixed tau s. So del ui at fixed tau s, and b is the usual b host operator, okay, and similarly b bar. And these integrals, okay, are along Cs. Let me write it here. Okay. And these include 1 over 2 pi I factors. Okay. So the normalization is that integral d sigma s over sigma s is 1, and integral d sigma bar s over sigma bar s is 1. No, for fixed I, because there is a I here, derivative with respect to ui. Is clear? The definition is clear. This is an operator that I am introducing, okay, on the Riemann surface. Now we take V1 to Vn, a set of vertex operators, not necessarily QB invariant. Okay, so we don't demand that these vertex operators have to be BRST elements of the BRST homology as yet. Okay, but it should satisfy these conditions. B0 minus Vi is 0 and L0 minus Vi is 0. These are needed because without these, you cannot really define a consistent correlation function of this vertex operators on a Riemann surface. Right? The correlation functions become multi-valued. Now we'll define a P form. Define a P form on MGN. Okay, as follows. So this form will be P form will depend on the vertex operators. Let me also put all the normalization factors here. So this correlation function is the correlation function on the moduli on the Riemann surface. Okay, this Riemann surface is what I introduced earlier, right? It obtained by the collection of transition functions, right? So a given Riemann surface is characterized by a particular set of values of u, okay, which means a particular point in the moduli space. And now what we are saying is that we introduce a P form on MGN, okay, by writing this. So this is in terms of given in terms of the correlation function on that Riemann surface of these operators. The B's that I have introduced here, these are the B hosts, okay, and the set of V's. Pardon? No, there are no extra C hosts. V's have C hosts. V's are BRST. I mean, when you take V to be in the BRST elements of the BRST homology, they'll automatically have the C host, right? But not 3. N. Each of them will carry the C host. Where is? No. So omega is the P form. This is all one line. Yeah. Omega is given by this. Yeah. This times this. The definition is clear.
Can you argue why you need APIs like inside this like vertex operators like find correlation, but why we need to take that input?
Because okay, first of all, we need something which is a form, right? It should carry some I index. Without the B's, there will be no I index. Okay. But you can also argue that how many B's you need, you can argue from ghost number conservation, right? Because you see each of these, I mean, for physical states, each of them will have ghost number uh, 2, right? So at 2n, ghost number 2n coming from here, right? On a Riemann surface, you need ghost number 6 minus 6g. Okay. And the B's basically, so for P equal to 6g minus 6 plus 2n, right, which is the relevant one, that's the form that we need, right? It will have the correct ghost number. We will see for the sphere how it works, right? Sphere 4-point function will also be given by this structure. Is this definition clear? Are there questions? Yeah, exactly. Yeah, but the reason that I have introduced it is it will become clear in a few minutes, right? Why I have defined it for generic states. Yeah, so maybe I should say, yeah, maybe I should have said this. So V's, as I have already said, are basically the punctures. So VA is inserted at WA equal to 0 in the WA coordinate system. Okay, so they are basically the punctures. Okay, but it's not just enough to say that they are the punctures. If you are considering V, which are not necessarily dimension 0 primaries, we also have to say which coordinate system we are using, right? And we introduce the notion of changing coordinates, right? If you remember that F circle V is what changes coordinates from one coordinate system to another coordinate system. So the V's are inserted in the WA coordinate system. So if they are kept at WA equal to 0 and they are inserted in the WA coordinate system, if you want to evaluate the correlation function in any other coordinate system, you have to find the relationship between the other coordinate and WA and make appropriate transformations. Okay, if Z is f of WA, right, and if you want to evaluate it in the Z coordinate system, then what we insert in the Z coordinate system is F circle WA. Is this clear? And now I can write the amplitude. So S matrix or amplitude is given by GS to the 2G minus 2 plus N. This is the string coupling. So this form, okay, if now you set P equal to 6G minus 6 plus 2N. Okay. That is the form that you have to integrate over the Riemann surface to get the amplitude. Now one useful identity that omega satisfies. So omega P Gn V1 to Vn satisfies sorry, I had written it the other way. P form QB okay. So NVI is basically the host number of Vi. Okay. And here I have defined this omega for arbitrary V1 to Vn. Okay. But of course, if the host number doesn't add up correctly, it will give you 0, right? Because on the genus G Riemann surface, the total host number better be 6G minus 6. Is this statement clear? Right? So this P omega P, okay, after summing over basically action of QB on each one of the vertex operators separately generates something which is an exact form. Okay. Now I'll not give the proof, but let me just indicate how the proof goes. Okay. So you see here, suppose you apply QB V1 and then rest, then V1 QB V2 and then rest and so on. Okay. That is effectively taking all the V's and doing a integral of the BRST contour around all the V's. Okay, because that's what this is. Okay. Now this integral over BRST contour on the Riemann surface, you can take it away from these vertex operators and try to shrink it to a point. But in that process, you will pick up the contribution from the commutator of the B's with Q's. But commutator of B with Q, okay, you see there is a Bi is given here, right? Commutator of B with Q will be determined in terms of commutator of the small b with Q, and those are the energy momentum tensors. We had seen that QB with B anti-commutator is the energy momentum tensor. Okay. So effectively, this what it does, okay, that if you sum of if you do this integral, okay, and move the contour around, what it does is it basically replaces one factor of Bi, okay, by Ti. Okay, where Ti means you replace B by T. Okay. But inserting energy momentum tensor, okay, essentially involves corresponds to deforming in the moduli space, right? Okay, energy momentum tensor is the generator of diffeomorphism on the world sheet, right? And by working through it together carefully, one can show that replacing one B by T, okay, basically amounts to taking a derivative of omega with respect to Ui. Okay, so you get P omega P minus 1 because one B is gone from here. Okay, you replace it by T, and the effect of the T essentially is a derivative with respect to Ui. Okay, and that's where you get this T. Okay, that's basically the logic as to how you get this. Okay, but the full derivation requires doing this carefully, keeping track of all the signs, etc., which I will not do. Okay. I'll now explain why this is useful. So consider this now, omega gn. Now we are considering physical 6g minus 6 plus 2n. Okay, and now we are going to take QB Vi equal to 0. Okay, so these are BRST invariant operators. So what I have done is that I am now considering physical amplitudes. These are all BRST invariant operators, except that the first one I have taken a pure gauge. Okay. So now apply this result with V1 replaced by lambda. But all of these now vanish because V2, V3 up to Vn we have taken to be physical, QB on Vi equal to 0. So it says that omega of QB lambda V2 to Vn is just given by the right hand side. So this will be given by d omega gn 6g minus 6 plus 2n minus 1 lambda V2 to Vn. So it becomes an exact form on the moduli space. And so now if we integrate, this becomes boundary terms. And these boundary terms one can ergo vanish, can be shown to vanish separately, which I will not do. And this then immediately shows why pure gauge states decouple from the S matrix, right? In a general genus Riemann surface, right? This identity is good enough to show decoupling of the pure gauge states. Is this clear? Any question on this?
So, like for foreground amplitude, this is just keep the gauge invariance from the
Yes. So for 4 graviton amplitude, it will give the gauge invariance of the amplitude. That if you replace one of the gravitons by a pure gauge, right, longitudinal polarization, then it will give you 0. Okay, now I think so far it has been somewhat abstract, so let me give some example. Okay, this many of you may be familiar, but I'll now see how the familiar result comes out of this analysis, and I'll be doing it in two different ways using two different parameters of the moduli space. Okay, to just to illustrate the point. Okay, first I'll do the easy one. So a sphere 4-point function, right? So you take okay, so this is d1, d2, d3, d4, and s1, s2. and circles, let me draw C1, C2, C3, C4, C5. Okay. So we take transition functions. You have to introduce two complex parameters. Sorry, one complex parameter. I can do it in any way I like. Okay, so I'll do it in the way that makes life simple first. On C1, take Z1 equal to W1. On C2, on sorry, not on C1, where did C1 on C2, Z equal to W3 plus K1. This is some constant. On C3, on C4, yeah, this is Z refers to a sphere, yeah. So on this we are using Z1, on this we are using Z2. Yes, we start a Q1. I'm going to do the Q1 afterwards, which will be a little more complicated, right? But the final result will be the same. And on C5, I take Z2 equal to W4 plus Q. Okay, and Q is the parameter. We are going to treat Q as a parameter. Okay. And I'll also choose these physical vertex operators as of the form C bar VMI. So the amplitude will be Gs to the power 2g minus 2 plus n, so ds square, and then you have minus 2 pi I. Okay, so let me, this is 2g minus 2 plus n. This coefficient is minus 3g minus 3 plus n. Okay, so g is 0, minus 3 plus 4, so minus 1. 2 pi I minus 2 pi I inverse integral m04 we are going to use q and q bar as independent parameters. So this is write the integrals. Okay. Now we are going to do it in the Z plane. Okay. So the positions, so V1 at what point in the Z, so we'll use the Z1 plane. Okay. So on C1 we have taken Z1 equal to W1. So V1 at Z1 equal to 0 because it's a W1 equal to 0. V2 at, you see from here V2 is at Z2 equal to K2, but Z2 is the same as Z1. So V2 at Z1 equal to K2, which is also equal to Z2, and V3 at V3 at Z1 equal to K1, and V4 at Z2 equal to Q, so Z1 equal to Q. Okay. So CC bar V1 at 0, CC bar V2 at K2, CC bar V3 at K1, CC bar V4 at Q. Is clear? This is in the Z1 plane. We are working in the Z1 plane. Okay. So you have to figure out what the BQs are. So BQ is sum over S. Let me write the general expression first. Sum over S integral over CS del Fs tau S U, or I can write Q, Q already has two parameters because it's complex, tau S Q by del Q plus okay, this is a general expression for BQ. Now you see the only Fs that depends on Q is this one, right? C5. So this is going to be integral over C5 del Fs del Q is simple, right? It's just Q because this you can treat as sigma 5 and this as tau 5. And Z2 is the same as Z1. Okay. So this is basically dZ1 bZ1. This vanishes, okay, because Fs bar, okay, if you complex conjugate Z2 bar is W4 bar plus Q bar, right? So the Q derivative is 0. So this is 0. Similarly, BQ bar will be integral over C5 dZ1 bar B bar Z1 bar. Is clear? Okay, this is simple enough. So if it's not clear, please ask. Okay, it's just applying the whatever I had introduced earlier, the definition of BI in this particular case, right? And we are using the fact that only Fs that depends on Q is the F5, is yeah, F5, the transition function across C5. Pardon? DQ bar. Oh, yeah. No, it's, yeah, that's the point. It's not Q bar. See, the point is our modular space coordinates are Q and Q bar. Okay. So when you are defining BQ, right, we always define with respect to Q, right? That's why the second term is 0, right? The BQ bar will have a del Q bar. There the second term will contribute, the first term will not contribute. Okay. So one should distinguish between these modular space coordinates. You don't have to even given them a complex structure, right? I could have used the real part and imaginary part of Q, okay, using that definition. But here you think of Q and Q bar as independent. But when you have written BQ, the derivative is always with respect to Q, not with respect to Q bar. Yes, you are still summing over S, but only one S contributes, right? Because none of these have Q dependence. So only the F5 has Q dependence, and that's what I have written there. C5, you can easily see, is the contour around the fourth puncture. Okay, so let's then write the answer. So the amplitude is GS squared times minus 1 over 2 pi I integral dq OH dq bar CC bar V1 M. These are all M. Sorry, I should have. These are only matter parts, right? Because I have already extracted out the C and C bar. CC bar V1 M at 0. Then the next one at K2. CC bar V1 VM 3 at K1 CC bar VM4 of Q. Okay. And around this there is a contour integral of B of Z1 dZ1, sorry, and B bar of Z11 dZ bar 1. Okay, so is there a question? Pardon? Sorry, this is 2. Yeah, thank you. Yes. Yes. When you are, yes. So I am not using that parameterization in this case, right? Here I have introduced the Q parameter in the showing between the sphere and the disk. Okay. I'm going to do that later. Okay, that will be a little more complicated, but final answer should be the same. So here the Q parameter that I have introduced, that there is no Q in this showing these two sphere, between these only Q is here. Yeah, so I'm not using that parameterization of the moduli space, right? As I said, that is a one particular way of parametrics in a moduli space, right? But that's not what I'm using here. Here I have introduced the Q just as a relationship between Z2 and W4. Okay? Because as I said, I can introduce it in any function that I like. Okay? And I have just chosen to do it between Z2 and W4. Is this clear? Okay. And so now basically what happens is that this B, so this contour is around Q, right? This, because as you can see from here, that this is around the position of the vertex of order 4, right? And the vertex of order 4 is at Q. Okay. So now this integral B bar Z bar 1 C will pick up, will get a pole. This has a pole at the position of C bar. This is all Q. So we get essentially integral dz1 1 over z1 minus q, integral dz1 bar 1 over z1 bar minus q bar times Vm 4 of q, well q bar. Okay. So these give you 1, this is 1, and I think there is a minus sign. Right? The minus sign comes because we have B bar, and the B bar has to go through the C to first pick up the pole from C bar, right? And then the B will pick up the pole from C. There's a minus sign. So after you combine all that, what we get is pardon? Yeah, exactly. Yeah, yeah. This one exactly. That's where the B's are coming from, right? And I'm using the fact that because this contour is around C5, right, which is the contour around Q, right? I just pick up poles from these positions, the position of Vm4, right? These are untouched, right? Because you are not the integration is around the vertex of water Q at Q. So we get an amplitude as Gs times Gs square 1 over 2 pi I integral dq wedge dq bar okay, and this is the form which many of you may be familiar with. We fix 3 vertex operators and integrate over the 4th one, okay? And you put C and C bar on at the positions of the 3 vertex operators. Is this okay? Okay, now I want to do quickly the other parameterization, because since I had used that one, and then I'll stop. Pardon? Ghosts are inserted, no, at K2. I mean, these are at the origin. They are part of the vertex operator, right? So here these are at K2. Here these are at K1, right? And this one has no ghost because the ghost got stripped out because of the P integral. Those are the boundaries of the moduli space, right? Those have to be given special treatment. So often you can get away by using analytic continuation, but in some cases, as I said, you cannot use analytic continuation, and their string field theory has to be used to make sense of those divergences. So let's do the second approach. Okay, this time I'm going to use the kind of parametrization that I done earlier. Okay, so transition functions. On C1, we put Z1 equal to W1 plus A11. Okay, this is just a constant. So C1 is from the Z perspective, it's a circle around A11. So we identify Z1 and W1 by this. C2, we take Z1 as W2 plus A12. On C3, we take Z1 minus A13 equal to Q over Z2 minus A23. C4, Z2 equal to W3 plus A21, and C5 Z2 equal to W4 plus A2. Look at this is the kind of parameterization we had used last time. We had described earlier, right? The only transition function that depends on Q is this one, right? Between Z1 and Z2, okay, which you can see is here. So let's look at the vertex operators. So in the Z1 plane, V1 is at Z1 equal to A11, right? W1 equal to 0. V2 is at Z1 equal to A12. V3 is at Z2 equal to Z2 equal to A21, and V4 is at Z2 equal to A22. Okay. But you want to convert this into Z1 plane. Okay. So V3 is at Z1. You see from here, we can find a relation between Z1 and Z2, right? Say Z1 equal to A13 plus Q over and V4 sorry, yeah, it's clear. So these are the positions in the Z1 plane. V1, V2 is here. Pardon? Yes, but those are all constants, right? You can take them to be 53, 10, 0, anything that you like, right? I mean, those are constants. Q is the only parameter. And the idea is the final result should be independent of those constants, okay, which will not be trivial to see, but this will be left as an exercise, okay? But I'll write the expression first. Okay. Now, BQ, right? Let's calculate the BQ. BQ is, you see, the only transition function is that depends on Q is this one, right? So we write this, okay, across C3, this is integral C3 del F3 del Q B sigma 3 B sigma 3 plus integral C3 del F3 bar del Q B bar sigma 3 bar T sigma 3 bar. Okay. So I take sigma 3 as Z1, and tau 3 as Z2. Okay. So the relationship between Z1 and Z2 you can see from there. Okay. So sigma 3 becomes A13 plus Q over tau S tau 3 minus A23. Okay. So then this is our F. So del F3 del Q is 1 over tau 3 minus A23. I write in terms of Z1. Okay. So 1 over tau 3 minus A23 is Q inverse times sigma 3 minus A13, okay, which is Q inverse times Z1 minus A13. Is this clear? Okay, I just calculate del F3 del Q using this formula. Okay. I get 1 over tau 3 minus A23, and then I use the relation between sigma 3 and tau 3, okay, to rewrite this in terms of sigma 3 and A13 and use the fact that sigma 3 got Z1. Okay, that's what I've done here. And similarly for del F3 or del Q bar. Okay, so this part remains the same. Let me write these B integrals first. So this is integrals in our C3. Okay, we'll see in Z1 plane what it does. It's our C3 Q inverse Z1 minus A13 BZ1 BZ1. Okay. For Q there is no Z bar by the same argument. Then we have integral over C3 Q bar inverse Z1 bar minus A13 bar B bar Z1 bar DZ1 bar, and then CC bar VM1 Vm1 is at A11. That's there A13 plus Q over A12 minus A23. And this C3, let me write C3 surrounds okay. So this means it encloses this point and this point. You can see it's clear from here, right? What this contour C3 is doing is to separate out 1 and 2 from 3 and 4. Okay, so in the Z1 plane, C3 is basically, so if you think of on the complex plane, on the complex plane we have CC bar Vm1, CC bar Vm2, okay, the various points, then CC bar Vm3 and CC bar Vm4, and this C3 contour basically surrounds these two. Okay, that is our C3. Okay, so you can manipulate this by picking up residues from these points. Okay, you can pick up residues from these points. Now this looks nothing like what we had before, but the claim is that this is exactly the same as what we had before. Okay. To prove this, I'll leave it to you, right? Basically, what you have to do is that you have to use the fact that on the sphere you have an SL2C invariance, right? You can put 3 points anywhere you like. Okay. So use the SL2C transformation to put 3 points in the same places where you had the original 3 points, and then you will find that the integration measure basically reduces to what we had earlier. Okay. But in general, it will look different. Okay, but it is exactly the same expression that we had earlier. Okay, that's somewhat non-trivial to see, but it is true. Is this clear? Yeah, that also this is on the plane, right? On the plane you have an SL2C transformation. So you can make an SL2C transformation to put these, see here for example, you can see that 2 of the vertex operator positions depend on Q. Earlier you had only 1 vertex operator position dependent on Q, right? But what you can do is you can make an SL2C transformation that keeps these 2 points fixed and takes this one at another fixed point, particular Q independent point. Okay. Then this will have a complicated Q dependence. Okay. And then by making a change of variable, right, you should be able to map it to the original integral that we had at that time earlier. So that's the point. That one can show that this integral is the same as the original earlier integral using SL2C invariance. Okay, so let me just end by giving an exercise. Again for sphere 4-point function. Find the integrand if we put the vertex operators at 0, 1, x and iy. X and y are real. Normally, we introduce the two parameters by saying that the position of the one of the vertex operators is free, that you integrate over. But you may decide that you want to integrate in such a way that two are fixed, the third one is on the real axis, and the fourth one is on the imaginary axis. How do you write the integration measure? And the idea is that you have to choose the transition function appropriately, so that the one of the vertex operators end up at z equal to x, the other one ends up at z equal to iy. Right? And then you use exactly the same formula, integral dx was dy, and calculate the correct integrand. Okay, so I think I'll stop here.